Right now, thousands of invisible messages are passing through your body. High-speed data from cell towers, GPS coordinates from satellites 20,000 kilometers away, and even the background radiation left over from the Big Bang.
We live in a world defined by the electromagnetic spectrum, yet for most people it's black magic. This is the world of RF frequency. I'm an RF engineer, and today we're going to demystify the magic. Welcome to RF 101. Radio frequency, or RF, refers to the oscillation rate of an electromagnetic wave in the range of 3 kHz to 300 GHz. But what does that actually mean? At its simplest, RF is the study of how we move electrons back and forth in a wire so fast that they break free and travel through space as waves. These waves consist of an electric field and a magnetic field, oscillating perpendicular to each other. This is why we call it electromagnetic radiation. An important concept from the physics is that electric field or current creates a magnetic field, as described by the Ampère-Maxwell Law, and also a magnetic field creates an electric field, as described by Faraday's law. In the RF world, everything is a trade-off between two things, frequency and wavelength. They are tied together by the speed of light. As frequency goes up, the wavelength gets shorter. This is why your 160-meter ham radio antenna is massive, but your 5 GHz Wi-Fi antenna is tiny. Understanding this relationship is the first step to mastering RF design. In standard electronics, a wire is a wire. But in RF, at high frequencies, a piece of copper trace isn't just a conductor, it's a capacitor, an inductor, and an antenna all at once. If your impedance doesn't match, the energy doesn't just stop, it bounces back to the source. This is VSWR, the enemy of every RF engineer. In low-frequency electronics, we don't worry much about the width of a wire, but in RF, the geometry is everything. You've probably seen the number of 50 ohms everywhere in RF gear. Why? This is called characteristic impedance. It's not the DC resistance you measure with a multimeter. It's a ratio of the electric field to the magnetic field as the wave travels. If your transmitter is 50 ohms, your cable is 50 ohms, but your antenna is 75 ohms, that energy hits a wall. Some of it reflects back into your transmitter. This creates heat, potential damage, and lost range. Mastering RF is, in many ways, the art of making sure energy has nowhere to go but out the antenna. A pure sine wave carries no information. It's just a hum in the void. To send data, a voice, a text, or a 4K video, we have to change the wave. This is modulation. We can change the amplitude. That's AM. We can change the frequency. That's FM. Or in modern digital systems, we change the phase. How does this look in practice? It starts at the source, where data is generated. A mixer slides that data up to a high frequency. A filter cleans up the trash harmonics we don't want. Then, the power amplifier, PA, gives the signal the muscle it needs to travel miles. Finally, it reaches the antenna, where the electricity is converted back into the electromagnetic fields we discussed earlier. Radio frequency engineering isn't just about old-school radios or walkie-talkies. It is the invisible backbone of the modern world. Every time you tap your phone, every time a self-driving car senses its environment, and every time a space probe sends photos back from Mars, you are witnessing the triumph of RF engineering over the chaos of physics. It is a field where theory meets reality, where a fraction of a millimeter in a circuit trace can be the difference between a perfect signal and total silence. If you've ever looked at a circuit board and wondered how invisible waves actually work, you're in the right place. Our goal here at RF 101 Explained is to take you from the basics to advanced design. If you found this primer helpful, hit the like button.
It tells the algorithm that engineering content still matters.
But understanding the wave is only half the battle. In the next video, we're diving into the tool that terrifies most students but empowers every pro, the Smith chart. I'll show you why this 1930s invention is still the most powerful tool in an RF engineer's kit. I'll see you in the next one.